Hello, and welcome back to the course, to the second lecture. So we're going to do an introduction to differential equations, what they are, how they're used, and so on. And again, this is a course based on the textbook that's available at this URL. You can get a PDF, you can look at it as web pages, or you can buy a copy, and that's really the best way to support this project. It's an inexpensive paperback. All right, so this might sound kind of lofty, right? But mathematics is the language of science, right? That's what everybody always says. And the differential equations, well, they are the most basic and important part of this because, all the laws of nature and physics and all that are written basically as differential equations. So understanding differential equations really makes you understand how nature works. Especially once you have, once there are things that change. That's the, so where do you need derivatives, which is essentially everything. So, and you've really already seen and solved differential equations in calculus. I mean, you found antiderivatives. That's, a lot of what calculus was, right? So it is not really new. It's just a little bit more complicated, what we're going to look at. But it's essentially sort of a continuation of calculus. So an example that you may not have seen in calculus might look something like this. Right, and this is, this could come up, for example, with, I guess, different constants here. The constants are very, very simple. Like it could be the Newton's law of cooling. So how does maybe a mug of coffee cool down, if you have ambient temperature? But here, the ambient temperature is not just constants. It actually varies with time. Right, so it's x would be the temperature and t would be time. Right, so x is the dependent variable. So x is something that depends on t, and you can see that we're taking derivatives of it. Right, so x is going to be a function of t. Right, once you know t, you know x. Right, and it's really well if it's the temperature of the coffee at a certain time. Well, given any particular time, we have a temperature, right? Okay, so x is the dependent, t is the independent variable, and if you have, well, so, here if the dependent variable appears as a first derivative and as itself, so the highest derivative that appears is the first one, so it's a first order differential equation. All right, now what do we do with an equation like this? Well, one of the things that we want to do with a thing like this, well, we want to solve it, right? What is a solution, right? Now you want to solve it for x. It's going to be x in terms of t, right? So x is going to be some expression in t, right? Some function of t. So we have to figure out what this function is. Now, what does it mean for it to be a solution? It means that if we plug it back in, if we take this expression for x, right, and we plug it into this formula, right, the equation is satisfied, right? So if we figure out what x is, we take the derivative and we plug in the derivative here, we plug in x here, and well, if we get 2 cosine t, we're good. That's what a solution is, right? It's something that satisfies the equation. Well, I claim, and so a lot of this course, vast majority of this course will be basically how do we find the solution? It's not so easy, but let's just suppose that we somehow knew it. We could guess it maybe. Maybe we guessed that it's cosine t plus sine t, right? So that's we claim that this is a solution. How do we know it is a solution? Well, we plug it in, right? So here, let's start on the left-hand side. I mean, I have an equation, right? So compute the left-hand side, compute the right-hand side, are they equal, right? Right-hand side is already in terms of t. Left-hand side, well, it's in terms of x. I know what x is. I plug that in, right? So if I plug it in, well, if I take the derivative of this expression, it's minus sine t plus cosine t, and then I have plus x. So that's cosine t plus sine t. Okay, so I, look at this and I notice, well, the sines cancel, and then I have two cosines left. So I have 2 cosine t. Well, that's exactly what's up here, right? Yay, we have a solution, right? It is a solution because it satisfies the equation. Now, here's another solution, right? It's almost, looks very similar. I just added a plus e to the minus t to it. Well, let's try it. Let's see what it does. So we have, so we start on the left-hand side again. We just basically, just plug in wherever we see x or derivative of x, we just plug in the equation and see what we get, right? So we plug in, this is the derivative. Now, it's very similar up here. Because of the chain rule, I get minus e to the minus t, and then I plug in just x here. And now you notice, well, the signs canceled, but also the exponentials canceled, right? Because when I took a derivative here, I got a minus sign out of it, right? So when I added the two, the exponential just disappeared, right? So I'm again left with just these 2 cosines on the right-hand side. Yeah, and that is the right-hand side. So yeah, we do have a solution. This is another solution. So I have a solution and another solution here, right? So I have 2 solutions, right? So it's definitely, the solutions are not unique, it seems, right? Now, all solutions of this equation, right, look like this. So we almost got all of them, right? It's just, there's an arbitrary constant is allowed there, right? And this is really, if you remember to calculus, right, your instructor probably, made a big deal about always adding a plus c, and took off points when you forgot it on the exam if you didn't write a plus c, and made a big plus c with a exclamation point, right? Don't forget this. That's the c, right? I mean, here it's at a different place. It's not plus c, right? It's multiplying part of the equation. Yeah, but it plays the same role. So again, just like when you just solved an antiderivative, which is a very simple differential equation, it's going to be actually the first one that we look at in next lecture. You get there is a constant, then it always appears as plus c, but in general the constant might appear in different places, right? So here it appears, it's multiplying the e to the t, and it's really important to have it there because we're if we just have the equation, we want to find all solutions, because we're going to then be looking for some particular solution, the one that we're actually interested in, and that might be for some particular c. And if we don't put the c in there, we won't be able to solve, right? Okay, here are some graphs of these equations, of these solutions. Sorry. So here, 3 particular solutions are graphed. They start at different points, and then you follow what this expression is telling you, right? And here it's actually what's happening is that so these are for certain particular c's, right? Certain particular constant c, and so what's happening here is that the e to the minus t is decaying really fast. So you're really getting close to this thing, right? So you can see that on the graph, right? So you're getting lots of different solutions, right? If you find, in this case, all the solutions, right? So it's what is going to be called the general solution. All right, and finding solutions is hard. There's no completely general method. You cannot just sort of turn a crank, put the equation in into some method and turn a crank, and out comes a solution. I mean, that didn't even work with in calculus, right, for finding antiderivatives. So how could it possibly work here? All right. Now, for simple cases, or if we're somehow lucky for even some complicated cases, we can find exact analytic solutions. And when we can, it's great. It's we should be very happy to do so, and we should try to do that, right? But it's going to be, well, not always. I mean, again, just like in calculus, you couldn't always find a nice closed form solution for every antiderivative, right? Now, in complicated cases, or even some sort of simple-looking cases that we're sort of unlucky, you cannot find a nice sort of closed form solution. Well, but we should be able to at least get numerical and approximate solutions, right? We won't spend too much time on how these work. It's sort of a whole science unto itself. How approximate, right? If you're getting something approximately, you really want to make sure that how close it is to the real solution, right? But basically, that's what we would be left with in a lot of cases. But if we can, we should try to find these nice analytic solutions, and that's what we're going to spend most of the time on in this course. So the entire process of what we're doing is we start with a real-world problem. You work at NASA, Boeing, or anywhere else. So then you get a problem, right? Your boss assigns you a problem that you need to solve, right? You need to figure out how much fuel the rocket needs. You need to figure out if the bridge, what's the maximum load that it can take, or you need to figure out what's the temperature of the coffee. It's actually tea in this mug, right? So that's the real world problem. So from the real world problem, you need to figure out what sort of physical laws, right, or how do you sort of describe the problem mathematically, right? So you give names to variables, right? You figure out some dependent, some independent variables that describe the problem, and you figure out how are these related, and so that's what you do in this step. You abstract the real world problem, you create a mathematical model, for problems that we're talking about here. There's going to be a differential equation or several differential equations relating those variables that you described. Now, that mathematical model, now you sort of, you can sort of forget about the real world problem. Although maybe you shouldn't always completely forget about it. It might help you have intuition, but now you're in the land of mathematics, right? And here we want to somehow solve, right? You want to find a solution somehow, either numerical or exact analytic solution. So that's what we're going to spend most of the time in this course on this step, on the solve step, right? And we're going to get a solution to this model, right? So once you have a solution to this model, so maybe this is a differential equation, so this is a solution to the differential equation. Well, this solution to the differential equation, well, you're not done yet, right? You still have to interpret what that means. Sometimes that's simple, right? Sometimes you were really, interested in what a value of one of these variables is, at some point in time or space or whatever. So then you just read it off. You still might have to interpret a little bit, what does it mean? Do you get that precisely? How far away from the real value you are and stuff like that, right? So there's still some, something left. But sometimes, that's there's a lot more left to, in the interpret stuff, right? Once you have the solution, what does it tell you about, how to actually build the rocket, right? You have this solution coming out of this procedure. What does it tell you? So those are sort of the three steps, right? And your boss is not interested in what you're doing here. Your boss is interested in the real world problem, right? Your boss gives you this problem, and your job is to solve it, right? It's to build the rocket, not how you do that. That's your job, right? All right. So let's do a very simple example of how this works, right? So this is the exponential growth model. So suppose we have bacteria on a petri dish, and it's a really large petri dish, so that we won't worry about, it's bacteria sort of, growing too large. And we're going to have some population of bacteria, right? I mean, there's a certain number of bacteria on the petri dish. So maybe at time 0, there's 100 bacteria, right? And 10 seconds later, there's 200, right? So how many bacteria will there be at time 60? So 60 seconds from the start. So 1 minute from the start of the experiment, right? It seems like maybe we're not giving enough information, but we're actually giving quite a bit. So let's assume that there's enough food and space for the bacteria. Like they're just gonna multiply, right? Or eat something and multiply, and there's enough space for them. This is a really large petri dish. So the rate of growth is proportional to the population because the bacteria divide, right? They multiply. They multiply by dividing, right? I'm not a biologist, so this is the limit of my understanding of biology. But the more bacteria there is, the faster the population will grow because more of them divide, right? So our model is that the rate of growth is proportional, so some constant times the population, right? Where k is some constant, should be positive, right? Now the solution, let's just, let's just suppose that's what it is. The solution is this, right? These are actually all the solutions. Can be constant times e to the kt, where k is this k, right? Where c is some arbitrary constant. Okay, let's check. Well, we take the derivative of p that pulls down a k by chain rule, and so that's kp. So yeah, that checks out. That is a solution to this equation. So now what? Now what do we do? So we have p is c times kt, c times e to the kt, sorry. But we don't know c, and we don't know k. But we know two things. We know that at time 0, p is 100, and at time 10, p is 200, right? So, well, let's plug in the 100. So p0 is 100. p0, if I plug that into here, it's c times e to the k times 0, which is just c. So c is 100, right? Now 200 is p10, and I already know that c is 100. So we have, so if I plug in this 10 into my solution here, right, with c being 100, right, then I get this equation over here. That's just, I've rewritten this equation over here, right? So 2 is e to the 10k, right? And well, that's easy to solve. I just take the logarithm of both sides, right? That makes it log of 2 is equal to 10k, and then divide by 10, right? So I get that k is log of 2 divided by 10. It's approximately 0.069, blah, 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 some other stuff. So approximately that. All right. So our solution, the population as time t is this guy, right? It's just approximately this, right? Okay, so here is a model of it, and it's called the exponential growth model because, well, it looks exponential. So it is an exponential, right? Here, it sort of doubles every fixed amount of time. Now, P60, which was the thing that we were interested in, how many bacteria there are in 60 seconds. Well, we just plug in 60 into this formula, right? That's over here, right? And we get 6,400. So at 1 minute, there are 6,400 bacteria. Is that exact? No, right? That can't possibly be exact. And I'll give you one reason why this formula cannot be exact, right? Because the number of bacteria is always a whole number, at least, right? And so it would really make no sense if 61 seconds you'd get 6,859.35 bacteria, right? So that would be like a third of a bacteria, right? So it can't possibly be exact, but it's even if you rounded it up, it won't be exact, right? This is an approximation, right? You'll always get an approximation. Now, it's how close it is to where it is. Well, that's where the interpretation comes in. How do you interpret this model? How many simplifications did you make when you were abstracting, right? So, for example, we assume that there's enough space, there's enough food, and we assume that there's no, nothing else is going on. It's just that the bacteria is procreating at a fixed rate, right? So we made a lot of assumptions, so if we made them wrong, right? If they're not quite exactly right, then this is probably gonna be maybe wrong after a while, right? Or it might not be as close to the real answer as it was maybe at first, right? Well, but this requires understanding the problem a lot more, right? So interpreting what the answer is actually kind of hard, right? And it takes interpreting everything together. Like it's how did you abstract? What did you leave out, and so on and so on, right? So interpreting can be hard, but approximately, yeah, it's probably going to be approximately this, right? As long as our assumptions were approximately correct, right? So obviously only approximate, right? And how approximate, again, that's the harder question, right? But hopefully, if we haven't made too many simplifications, it's pretty good, right? Okay, now typically in these problems, the K is known. The equation is completely known, so you only need to get the C, and so for that you only need one condition, at least for these first order equations. So you only have an initial condition. You have an initial condition, almost, it makes it sound like there's time involved, and that's really what, where the naming comes from. So we have a condition at one point, right? So maybe at t equals 0, we have 100, right? That's an initial condition for the equation, right? So let's make a simpler example. Let's suppose that p prime is p, so let's just say k is 1. So if that's the equation, then these are all the solutions, so we're going to call it the general solution, right? It's basically I'm writing down all the solutions to an equation. So that's what the general solution is. Now, once I solve for the initial condition, I get a single solution, namely this one, 100 e to the t, and that's called the particular solution, right? It's the particular solution solving this initial condition, right? All right, so let's end on, there are sort of several equations that appear all over. So I'll call them the 4 fundamental equations, and kind of 2 of them are kind of the same equation, but I'll just, write them separately. So here, y is going to be the dependent variable, x is the independent variable. So again, one thing to get used to here is that the variables get named different things, and something, x will sometimes be the independent variable, sometimes the dependent variable. So you always have to be able to tell from either looking at the equation or looking at the problem, what are the dependent and what are the independent variables. All right, so here is the first equation, right? It's the exponential growth model, right? It's basically the one that we saw, and the general equation, the general solution, is this: c to the e, c times e to the k x, right? Now it's almost the same thing. Now, basically, if I allow this k to be also negative, then I could just write down the same equation, right? But let's just say it's it's a different equation. So we have exponential growth and we have exponential decay, right? So the exponent here is negative if the constant in front of the y is negative, right? Okay, so let's look at something that we haven't seen so far. Hey, it's a second derivative here, right? So the second x derivative of y, right? And I have now let's start with a negative, negative constant in front, and I'll write this negative constant as minus k squared, right? So k. Let's make k positive. It could be negative. It doesn't really matter. But minus k squared is always negative, right? So I have this this negative constant in front of the y, right? And then the general solution looks like this, right? I have a constant c1 times cosine kx plus constant c2 times sine kx, right? Now there are two constants, c1 and c2, because this is a second order differential equation. There is a second derivative, right? Now here's another one that looks very similar, the fourth fundamental solution, again second order, but now I have a positive constant in front of the y, right? So I'll write the positive constant as k squared, right? Then the solution that we have, the general solution, is going to be c1 times e to the kx plus c2 as e to the minus kx. It sort of looks like, a combination of these two, and that's really where it comes from. Another way of writing that is write it with some different constants. So let me maybe call them d1 and d2, with a hyperbolic cosine and hyperbolic sine instead of the exponentials, and that's sometimes more convenient than the exponentials, but we'll see on the next slide. They're the same thing. It's just a different way of writing the same thing. So these are what I call the four fundamental equations, and their solutions, their general solutions. And it's good to just remember these, right? Because they come up a lot. So it's good to just know what they are. And really, one could just say, well, there's no real method here. I mean, you just guess, and this is what they are. You can get them by one of these methods that we're going to be talking about, but really, these are so simple that you could just guess. One more thing to maybe again emphasize for these second order ones is this is k squared and this is k. Right, same here. This is k squared. This is k. This is minus k. Right? So really, if you had just some negative constant here, maybe if you have had negative 9 times y over here, right? Then over here you'd get cosine of 3x because you'd have to take the square root, right? Okay, so that's something to keep in mind, right? That you're really taking a square root of this thing. And that's why I'm writing as k squared, right? So that I can easily write the square root by just writing k. All right, so what are hyperbolic sine and hyperbolic cosine, because some of you might not have seen it, and really by definition, they just have, these are the formulas. Sorry, I dropped my pen. So those are just formulas. So these have some properties that they sort of act like cosine and sine a little bit. So that's why they're called hyperbolic sine and hyperbolic cosine. They're not quite sine and cosine, but some of the properties are very similar. So for example, cosh, the hyperbolic cosine, at 0 is 1. Sinh, the hyperbolic sine, at 0 is 0. It's just like sine and cosine, right? They do the same exact thing. The derivative of cosh is sinh. Okay, here is a little different, but very similar. And the derivative of sinh is cosh. Again, it's little different, but very similar, right? There's a minus sign missing here, but other than that, this very much looks like sine and cosine, right? Now, and it's really that minus sign that why these are the solutions of the fourth fundamental equation from the previous slide, right? When I had a positive constant in front of the y, and that minus sign is the one that gets you, why sine and cosine are the solutions when you get a negative, right? So, all right. So these are sort of they're a little bit nicer to differentiate, right? I don't have to keep worrying about like the minus one, right? But other than that, right? It's that's just what it is. All right, now the shape of the graph of cosh is kind of an interesting thing. It's called a catenary. It's actually if you have a hanging chain, that's the shape it will do. It's also the best shape for a freestanding arch. So the arch in St. Louis is actually an inverted cosh, and somewhere inside there's this formula. This is the formula. This is the graph of the arch, right? So this precisely gives you the arch, right? Let's look at the graphs of this. So sinh looks like this. It goes off to infinities. To x goes to negative infinity, sinh goes to negative infinity. As x goes to plus infinity, sinh goes to plus infinity. So it doesn't oscillate like sine. It just does this. And cosh, well, it looks like this. It has this shape. It goes to plus infinities on both sides. And again, it doesn't oscillate. Right, so those are sinh and cosh, and they're really because they're just a combination of the exponential. So this is the exponential growth, this is exponential decay, right? So it's e to the x and e to the minus x, right? And when you combine them in two different ways, one with the negative sign, one without, you get either this shape over here, or you get this shape. Okay, now just for completeness, this is what sine and cosine look like, right? So sine and cosine, they keep oscillating, right? They go on like this forever. They don't go to plus infinity or minus infinity. All right, so that's it for today. So okay, see you next time.